Hey, hello.
Hello, sir. Good evening.
Yeah, hello. Good evening.
Uh, yes. How are you doing?
Yeah, I'm doing good. Yeah,
Okay, it's exactly 8.
yeah. So, shall we do? Like, what we usually do is we just quickly go through concepts in the weeks 5 to 8.
Okay.
What we usually do in the session, revision sessions.
So, like a snapshot view. It's revision only. So, yeah.
Yeah, yeah.
Okay.
But yeah. So since no one else has joined, yeah. If you have any specific questions, we can also discuss that.
Yeah, I was having some issues in week 8. Uh,
Okay.
yes. There was this question on change of basis, which I mean, a change of basis I was able to handle back in week 1 to 4 linear combinations and all.
Okay.
But now I think it's slightly different in the context of eigenvalues and eigenvectors.
Right. So which question is there? A specific question you are
Yes,
talking about?
just a second. I
Yeah.
will. Okay, so the deadline is over, so we can go to the graded assignment also, right?
Yeah.
Yeah. So week 8. Uh, Question number uh, 7, 8. Uh,
Okay. 7.
7, like if you could just like show me how to think, the thinking behind the solution, basically.
Yeah.
Yes. So maybe you can present.
7, 8. So what do we have? So we have 7. W is in R3, and we have two bases which are B1, U1, U2, U3, B2, V1, V2, V3. The change of basis matrix is defined by the transformation. Okay, so we take something in B1 to B2. Which of the following
So,
matrix is
so
here?
what I did was just write U1, U2, U3 as columns of B1, and V1, V2, V3 as columns of B2, and then do this and put them in this equation, basically. B2 is equal to B1. I think that's naive. I mean, like, what does it even mean, first of all, and then maybe we can.
Right, yeah. Okay, so let me first write down the basis. So U1
Yes.
is what? They are 102, 102, and U2 they have given it to be 0, 1, -1, 1, 1, 1. Okay, so 0, 1, -1, and U3 is 1, 1, 1, right? So this is B basis 1. This is B1. And B2 they have given it to be B1, V2, V3. So this B1, B2, V3. This is respectively 2, 1, 1 and 1, 2, 0 and 0, 1, 2, right? And what we have been asked to do is the change of basis matrix defined by the transformation where you want to go from B2 to B1, or sorry, B1 to B2, right? So if you input in basis B1, then you will have to go to B2. Okay, so how do we approach this?
Yeah, so I just wrote u1, u2, u3 as vectors in one matrix, and the other basis vectors in the other matrix, and just arranged them according to this equation. But that's probably wrong. I mean, it led me to the wrong answer
Okay.
for,
So
find, for finding P. By the way, what have been asked to find? Let me just check.
yeah, so we have to find P, right? So we have to find
P.
the change of basis
Yeah.
matrix.
Yes.
So okay, so let's say we have, let's first of all try to understand what we mean by this, right? So this is the vector W, some W is some vector and its representation in the basis B1. So for example, if W happens to be, so if W equal to say 102, right, which is the first vector U1, meaning W is, happens to be U1 itself, then you can write U1, which is, so this is the same as saying what is U1. Okay, let me just say, I'll just say let us start with, so start with U1 and try to express it in terms of the basis B1, right? So this is nothing but some linear combination of U1 plus alpha 2 U2 plus alpha 3 U3, right? So of course it's not equal to this, but we are writing just the coordinate. So it will just be, so I'll put it this way. So if U1 is alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3, then the representation of U1 in the basis B1 will just be alpha 1, alpha 2, alpha 3, right? This is in general, so this is not necessarily U1. So in fact, start with some W in R3, right? So you can start with any W in R3, and you can, since U1, U2, U3 is a basis, you can express W in terms of the basis. So the coordinates of W in that basis will therefore be alpha 1, alpha 2, alpha 3,
Yes. I
right?
think this much. Yeah, this much we have from week 1 to week 4 all day, right?
Right, yeah. So in fact, there is this has nothing to do with eigenvectors, eigenvalues as far as I can see.
Yes.
So,
Yes.
right, yeah, but see, so you can still go ahead and do this. So if you want to see P, right, P is something which takes a vector in
B1.
B1, right? So which is expressed in B1 terms. So first of all, for what will be U1 of, so U1 in terms of, sorry, this should be so this will just be 100.
Yes.
So and U2 will be likewise, U2 will be U again U1 in B1 is 100, U2 B1 is, okay, 010, and U3 B1 is 00, right? So this is your whatever is in B1. Now what happens is you have to represent U1 in terms of V1, V2, V3, right? So and that will go into the columns of P. So for example, let us now try to represent U1 uh, in terms of basis B2. Okay. So what will U1 be? So U1 we know is 102 in terms of basis. This is alpha. So I'll just use ABC because it's easier to write. So AV1 plus BV2 plus CV3. Sorry, this is CV3. Correct. So this is 102 in terms of AV1 in terms of basis B2. So this, do you know how to solve? Like this is just a system of equations. So A times this is A times the vector 211 plus B times the vector 120 plus C times the vector 012, right? So this is equal to 102. So we have to solve for ABC. So far, is this fine?
Yes, it is fine.
Yeah. Okay. So let's quickly form this matrix. So this will be the matrix the augmented matrix, right? So this will be the augmented matrix 2 1 0 1 and 1 2 1 0 0 2 2. Okay, we can reduce this, so we can maybe quickly reduce this. So this becomes 0 and minus 2 1 2. Okay, I'm just usual reduction I'm doing. So this may be 2 times, or what is the simplest way of doing this? Half times first row, I have to subtract, right? So if I subtract, then this becomes 0. This becomes 2 minus half. So that's 3 by 2, right? And 1 minus 0 and 0 minus half. So minus 1 by 2.
Now we have to get the -2.
Uh, which one?
Uh, no, I mean this. We are solving a system of equations, right? Just so I mean,
Yeah.
so
Yeah, so this so far it is correct, right? So we are just I'm just multiplying this by. So first step I did was one row 3 minus row 2, so that gave me minus 2 1 9 2. Now I'm doing row 2 minus half row 1, so that gave me 0 2 minus half 3 by 2 1 minus 0 and 0 minus half, right? So that gave me this one. So now this we have to further reduce. What we can do is we could have done something.
operate on -2 using row 2, right? So just add. Uh,
Maybe we can just multiply row 2 by 2. That will get rid of.
4 by 3 times. Uh, add 4 by 3 times of row 2 to row 3, right?
Yeah, we could do that, or we could maybe get rid of the denominators here so that uh, life is easy. Because so this is 3 by 2, so this 3 goes, this becomes 2, and this becomes minus 1. So,
Yes.
right, so that is done. What else can we do? We can, yeah, now we can, why are they giving so, it's not complex, but too many calculations.
Just multiply row 2 by 2 and row 3 by 3. Then add the.
Okay, so this becomes 0. So 3 times this, 2 times this. So 3 times this is 3, 2 times that is 2. So that becomes 7, right? Yeah, so 3 times this, 2 times that. So 6 minus 2 is 4, right? Yeah, perhaps we can stop here. So, and collect the answer. So this is what? This is, all of this was done for ABC, right? So this is ABC. So C is
4 by 7.
yeah, minus, is it 4 by 7? Yeah, 4 by 7. What is this? Minus 1.
-2 times this thing, which is like -8 by 7, -1 by -1, and then divide by 3. So we'll have to just work out maybe.
Minus 1 minus 8 by 7, right? Minus 15 by 7 minus 5 by 7, is it? Yes, 5 by 7. Is that correct? 1.
Yes, looks good.
So 1 plus 5 by 7 is 8 by 7. I think this should be 4 by 7. So if you look at it, I think first column, that's why they put the denominator as 7. So this should be 4 minus 5, 4. Let's go back. So, oh, they have given 6 minus 5, 4. I made a mistake here. So, what is the mistake? So,
So basically, then now I have to repeat for the other two columns and then just.
correct, yeah. But yeah, where did we go wrong? So, there's just 6 here. So,
Some calculation, but
uh,
otherwise the concept we have gotten right. So
Yeah. So, but just to be sure, I just want to make sure that so this is 2101. So 1 minus 1 plus 5 by 7. Oh, sorry, this is 7 plus uh, uh, okay, 1 plus 5 by 7. Oh, 7 plus 5 is 12, right? So sorry, yeah. So this is 12 by 2, 6. Yeah, correct. So this is 6 by 6. Yeah, that's the idea. So 6 minus 5, 4. So what you have to do now is express V2 in terms of basis B2, then V3 in terms of basis B2. So that will give you the other two columns.
Other two columns. Okay. Okay. Good.
Okay.
And can we like just to quickly go through like uh, uh, powers of a matrix in terms of like um, so this much I know that if we have a matrix whose eigenvalues are all strictly less than one, and then if we raise it to the power n and n tends to infinity, we take the limit, we get zero because the everything gets squeezed down to zero basically, right? Hello.
Yeah, sorry. Got
uh, okay.
Yeah, what- you are saying something.
Yes, I was talking about raising a matrix to a power uh,
Ah,
where where let's say all the eigenvalues are strictly less than one. Uh, then if we raise the matrix to power n, and as n tends to infinity, the matrix will go to zero, right? Uh, okay. Once again, I think we have some.
yeah, sorry, some internet problem. Yeah, so there was a power failure, so I had to rejoin and it's kind of.
Okay, maybe let's wait a minute and see if it is steady before continuing.
Yeah, I think now it should be fine. So you are saying raising a matrix to a power with fractional eigenvalues. Yeah.
Yes, eigenvalues all less than one, and then if as the power n tends to infinity, the matrix goes to zero, right?
Uh, yeah, right. If both the eigenvalues are fractions, then yeah.
Okay, so any other ideas like related to this? Because I saw like a lot of questions based on powers, raising matrix to a power, and then like computing the limit or something like that. So are there any like further ideas here, or I mean, as long as we know this property, we are good.
This should be good. Yeah. So as long as you know that the basic idea is if you raise a matrix to a power, then if it is diagonalizable, then you can raise the just the diagonal matrix containing eigenvalues to that same power, and you are done. And if the eigenvalues happen to be, some of them happen to be less than 1 in modulus, right, in absolute value, then you are lucky because you can get rid of one of those terms, right, in the limit. So that is about it actually.
Okay. Can we just visit this question 4 from week 8, graded assignment?
Yeah,
So there's a 5 by 5 matrix. Okay. My question was, okay,
yeah,
yes. Um, so um, so basically, in week 8, and also I think in week 7, but week 8 certainly we studied a bunch of properties basically, right? So which were like shortcuts, to answering this kind of question, right?
Mhm.
As opposed to having to do the whole thing manually. And
Mm.
and and, and I'm not sure that I'm up to the task with all those properties. I mean, my idea is that just to know the basics, from eigenvalue, eigenvector, and the realizability and everything, and then maybe so can we solve a problem like this manually? I mean, but it's a 5 by 5 matrix, so computing the determinant manually is like starting to get laborious already, right? I think even if it's 4 by 4, it can get tricky. Is there something like intermediate between fully manual and fully property based? Did I make sense?
Yeah, yeah. So I don't know if there is anything intermediate between the two. For instance, what will we do here? See, first, the last option is very easy because you just have to multiply and see, right? So there is nothing much there. And if
Yes,
you
that
add,
can
so
be.
one observation is this everything sums to 1, right, along the rows column. So that is why, in fact, 1 1 1 1 1 is an eigenvector, right? And 5 into if you just add 5 into 4, what is this? 5 into 6 by 2, right? So that is 15. So B and D are quite clear just by looking at the options, right? Now, tricky part is how will you find out if A is diagonalizable without actually computing the eigenvectors, eigenvalues manually, right? So did you solve
Yes.
this problem, by the way?
Sorry.
Uh, did you solve this problem?
No, actually, I mean, I think I skipped.
Okay, okay. So let me also think. So B and D are very easy. So there's nothing hard about B and D, but A is, at least A on the surface is not, it is not clear why it is diagonalizable because uh, let's see. So 1 2 3 4 5
How did you confirm B?
B. So see, the each row adds to 1, right? Each the sum of elements in each row is 1. Sorry, 15, right?
Yes, I mean, how is, yeah, 15 having.
So that means the sum of the columns are what? 15 15 15 15 15, right? So that is 15 times 1. So the 15 times this vector. So that is an eigenvector. So if you multiply
Oh,
A
okay.
into 1, so that is nothing but matrix into column, right? So if you multiply a matrix into a column, then this is nothing but what is this? Sum of the linear combination of the columns. So linear combinations of the columns. So if V happens to be any time, right? So if V happens to be the vector made up of ones, then this is nothing but sum of the columns. It's just 1 into column 1 plus 1 into column 2 plus 1 into column 3. So therefore, that is why you can easily see that the sum of the columns here is just 15 times this vector V naught again.
Yes, okay, okay. Okay, so using D, you kind of did this
Yeah, so
V.
here this is just option, just making clever use of the options. That is all.
Yes, yes, yes. This will.
So there is no other property per se, but A is diagonalizable. Let us see. Why should A be diagonalizable?
Actually, for me, the thing is, I actually checked this A option somehow very fast. So I think I had some intuition here. Whereas you were quicker to do B and D. So maybe
Right,
we
right,
could
yeah.
compliment here, but I am not able to recall what was that exactly. Yeah.
Okay. Mm,
Okay, so diagonalizability, we use this property, right? So all the eigenvalues must be distinct, right? Or the more general case being that the GM versus AM thing, that the GM has to be strictly equal to AM for each eigenvalue, right?
right. But
Yeah.
see, if the eigenvalues are
Yes, but the yes. So I think okay, I'll have
right.
And
So here,
the problem is that I didn't even take notes on this. I didn't even like solve this in the. I just checked it somehow. So 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 I don't know what on what basis I did that, but something there was that I was very confident of. So if I only I remembered, it would be so much better. But okay.
right. Yeah. So I am not able to see right away why this is diagonalizable because this is not.
The diagonal elements could they provide some clue like the okay but that's for the eigenvalues themselves.
Yeah. So
uh, Anything via trace determinant, okay, but determinant is still like the the long way, and
yeah,
there are no zeros or anything to help us. So
correct. Yeah. So there is that we cannot use.
is
Basis.
this is this a circulant matrix? I think right by definition. Maybe
What
that.
is? Have we covered circular matrices in this?
I think briefly there was. I mean, there were some problems, so I looked it up and I found this definition basically that
Okay.
you,
What is the definition?
you kind of rotate. See, I mean, every row has the same elements, but like rotated by one element, something. I mean, you
Oh,
can
okay.
see that. So 1 2 3 4 5, then 5 1 2 3 4, and then 4 5 1 2 3. So you see, this is just very clear pattern that I'm talking.
Okay. So each
So that
element apparently
yes.
shifted by
Yes,
one.
shifted by one position, right?
Okay.
So maybe circular matrix could hold the clue to this. So which I will check maybe. If
Okay. So okay. This is see. Ideally, this is then not strictly a part of the.
week 8, right? Till
Yeah,
week
it's
8.
strictly not a part of the syllabus because if you have to use that property has not been
So
covered. Yeah.
yes,
So it
yes.
was a part of.
Even I didn't find it like in the in the lectures that I watched.
Okay.
Maybe if it was there, somewhere hidden or like I didn't pay attention then. Okay, but
Okay. Okay. Okay.
fine, I think maybe we can just let
Yeah.
this
This
be
one is yeah.
just for now. If there are maybe more questions, then I will, maybe look this up separately. But otherwise, I think we are fine, right?
Yeah. This one we can actually yeah we can ignore this one because
Yes.
this
Oh,
requires.
yes. Because then I hope this won't be asked in the exam anyway, if it is not.
Yeah. Yeah. Yeah.
I mean,
Because this
sometimes
is
there are a question in the assignment that are ahead of the syllabus actually.
correct. Correct.
This has happened multiple times.
Yeah.
So,
Yeah. Yeah. You can ignore this one. Yeah.
so I won't be surprised if that's happening here again. Okay. Okay, then you basically said that you had some. Okay, it's already 8:30 and nobody else has joined. And hello.
Yeah. Yeah.
Yes, and we can continue for another 30 to 45 minutes max. So based on that, any how would you like to go about a quick revision, basically, which was the theme for this session,
Yeah.
right?
So quick revision. What we usually do is we just go through the theory once again.
Okay.
So just the main idea. Uh,
Yes, we can do that. That would be helpful, I think.
so main ideas would be what eigenvalues. I mean, I'm sure you would already know all of that. So maybe I just list them down, and if you want, we can discuss them.
Yes.
So what eigenvalues? We have eigenvectors. Then we have uh, properties of eigenvalues and eigenvectors. Then we have diagonalizability, right? So we have arithmetic, so algebraic and geometric. So maybe that will come here separately. Also, we can write
Yes, it should come before diagonalizability.
uh, densities of eigenvalues and diagonalizability, and you have what else do you have? You have
Then this shift from this transition from R2 to Rn, right? I mean,
right, yeah,
yeah, I
R2,
think that was a theme there. So yes.
yeah. So that we can probably just generally talk about Rn, and then we have, I think, determinant. Determinant is not
Oh
too hard,
yes, determinants and matrices. There was one week, week six actually, which
right? Yeah,
properties of determinant and also
yeah. So properties of determinant and
yes, this was right
matrix.
and transpose. Yes, inverses. But
Yeah, transpose.
yes. This was all week six actually. These
Yeah,
last. So,
I think that is all. That is roughly in the syllabus, if I'm not mistaken.
yes, I think so. Uh, I mean, I haven't gotten a good handle on week eight yet. But
Okay.
yes. Uh,
So what is there in week 8? Week 8 is geometric multiplicity, okay, regulation, properties, special and complex eigenvalues, eigenvectors. So I think it's roughly the same as week 6.
yes, iron thing, I think.
Sorry, week
So
5, yeah.
yes. One more was there triangular matrices, some properties of
Okay. So,
this was week seven slightly, yes. That's what,
yeah, right.
yes. And how they
Yeah,
like
so,
simply finding the eigenvalues and things like that.
right. So here I think we can, so we
And
can,
one more
yeah,
we can write like maybe the applications actually because it feels like quite a shift, from the theory to actually using the concepts to solve real world problems whenever they come. Uh, but
right.
but I think that's mostly it's like learning to map from theory to reality, or rather the other way around.
Yeah, so that is, yeah, best
Yeah,
thing.
that maybe doesn't need to be written separately, but yes, I mean
Yeah,
that is something that I assign a mental category to. So yes, I just thought to mention.
right, yeah.
Yes.
Okay, so this, I hope all this you already know, right? So eigenvector is one, so the eigenvectors and eigenvalues always occur in pairs. So there is a
Yes.
lambda comma v with v not equal to 0. So eigenvectors can never be 0. So,
It's the trivial. It would be trivial, right? So we don't count it basically, right? I mean,
uh, so for
no,
a,
no. Actually, no. That's for the eigenvector, yes, maybe, but yes, for eigenvalue, it's different, right? Where we have a full rank matrix, then no eigenvalue. Sorry, if the rank is if it's not a full rank matrix, then one of the eigenvalues has to be zero,
right,
because
right, yeah,
yes, because otherwise the product of the eigenvalues, which is the determinant, would not be zero, but which it has to be, since it is
right,
not a full rank matrix,
yeah, yeah.
and so
So
on.
that will, yeah, maybe that will go in. We can even call it one of the properties. So a lambda equal to 0 is an eigenvalue.
And maybe here where you wrote AV equals lambda V, maybe you can write in the determinant of A minus lambda I, because like because this is like slightly harder to use for finding the, but okay, it's the same thing, right?
Right. So this is just the definition, right? So
Yes,
then we come to the characteristic polynomial to find the
yes,
eigenvalue. So
yes,
that
yes,
is
yes.
by setting the determinant of a minus lambda to 0, and then we find the
And even for finding the eigenvector, we use this only, right? A minus lambda I form.
right. For that we use a minus lambda times v 0 and solve the corresponding system,
Yes.
right? So that is eigenvalues, eigenvectors definition, and then yeah. So I think the rest of it we could easily call it properties. So yeah, one thing that we saw is this one singular. The other one, which is very common, is of course this trace of A is sum of eigenvalues, right? So of a matrix. That is one.
Yes.
And, yeah, the determinant is
Correct.
the product, right? So this is the product, and also every matrix has n eigenvalues, so not necessarily real.
Every square matrix. I mean, by
Right, right.
default,
Yeah. This anyway. So whole thing is only for square matrices, right? So
it's all this.
yeah. So everything is only for square matrices. So yeah, not necessarily real. It could be complex.
Yes.
What else do we have as properties?
Yes, and then there were like some quick ideas around basically shortcuts, real versus complex and how they. But okay, I think we can leave it for here.
Yeah, yeah.
Because we want the main properties and using which we can like actually derive some of the shortcuts on the spot if needed.
Right.
So that is my preference basically, because
Yeah.
otherwise there's just whole lot to memorize, and as we solve the problems, some of the things naturally start to commit to memory, which is better.
Right. Yeah. Uh, so that is regarding the main properties of eigenvalues, eigenvectors, and then we have, of course, the multiplicity. So this is am, right? So am of lambda would be what? Am of
The number of times it appears as a root in the characteristic polynomial. I think that's the definition, but
right, right, yeah.
yes,
So the
simply we
number,
can say that, yeah.
yeah, number of times the lambda I. So this is, we call it lambda I. Then lambda I appears.
By the way, I still have a habit of like simplifying too much the characteristic polynomial, such that some lambda terms can have to cancel to find the other ones, but then I don't know which are the other ones, and I have to check it manually by substituting directly. Is that
Ah,
okay, or like, am I missing something there fundamentally in terms of the approach?
so somehow you have to factorize, right? So
Yes, yes. Because otherwise, finding one is better than finding zero, right? uh,
right, right,
uh,
yeah, yeah.
of course, if you could find all of them, that it would be there. But then we use these properties, right? So let's say there are three eigenvalues, right? And two of them I can find by factorizing out one of them, okay, to simplify. And then that remaining one we can find maybe using some of these properties depending on like
Right, right, true. That's true. Yeah.
determinant, right? So is that okay? I mean,
That seems fine. Yeah.
yeah, fairly okay, I think so far.
Yeah. Yeah. So that is the algebraic multiplicity. GM will be the
That's the number of linearly independent eigenvectors for any given. So yeah, this is like corresponding thing, right?
yeah.
For each lambda, we have to
Right.
yes, the
Yeah.
notion of AM and GM exist separately for each
Right.
lambda.
Yeah. So or you could even call this is the nullity, right? So the dimension of the null
Yes,
space, right?
there was also a formula actually. Yes, yes, this one.
Right. So this would also lead us to that. Uh, yeah. So that is that, and we have this inequality that right? So AM lambda I always greater than or equal to uh, GM, right?
Yes,
GM.
yes, yes. And which leads us to diagonalizability, right?
So
So
every
which is a subset of this condition basically.
right, right, right.
Uh,
Yeah.
the, uh, so the equal to sign basically.
Right. Yeah. So this was again motivated by matrix powers, right? So motivated by
Yes, PDP inverse that whole thing.
yeah,
Yeah, we were doing this like
yeah PDP, the PDP inverse where the
yes,
P has eigenvectors on the columns and T will be the eigenvalues on the diagonal, right?
diagonal, yes.
Of, A, sorry, of T. So I think yeah, there are again alternative ways of looking at it, right? So a matrix is diagnosable if and only if, or rather, I just say that if A has n linearly dependent eigenvectors, we could put it that way, or we could say, what else could we say about diagonalizability?
Each eigenvalue is distinct, right?
That is not necessary.
Uh, I think that's the quick check, right? But if that fails, then we have to
Yeah,
yes.
yeah. That's so. For example, for the identity matrix, it will.
It isn't. Sorry, it is not necessary, but it is sufficient, right?
Yeah, it's a sufficient condition. Yeah.
Okay. I have to like
So
pay attention to this.
eigenvectors. So in fact, here there is one other property, right? So eigenvectors corresponding to distinct eigenvalues, right? Corresponding to distinct eigenvalues are linearly independent. In fact, that is what leads us to this property, even, right? So diagnosability. So if you have distinct eigenvalues, then eigenvectors are independent, and therefore it is diagnosable, right? So this is true for any matrix. Any matrix which has distinct eigenvalues will have corresponding eigenvectors distinct. So we are kind of making use of that to,
But we just said that distinct eigenvalues are already sufficient to establish diagonalizability, right?
yeah, that comes from this actually.
Oh,
So this is a much more general property which has nothing to do with diagonalizability as such, because it is antecedent to that. So
okay,
you
okay.
can establish any, for any matrix which has distinct eigenvalues, not all of them distinct, right? So this doesn't say that everything has to be distinct. This just says that
Ah, yes, of
two of
course.
them are distinct, then those corresponding eigenvalues, eigenvectors are independent. So right. So that is matrix powers, eigenvectors, columns, eigenvalues, diagonals. If A has independent eigenvectors, and so do we discuss similarity in this course? Matrix similarity.
Similarity transform. S
Right.
A S inverse, right? That
Right.
I
Right.
think.
Okay. So then
Yes,
that.
in one of the lectures, yes, the professor
Okay.
discusses, and I think there
Okay.
were some problems also. I mean, the way I was motivated by this was that I wanted to do like row operations on the non-diagonal matrices to convert them into diagonal and then quickly find the eigenvalues, but which doesn't work, right? Because doing the rows operation changes the determinant or something like that, right? And which breaks the pieces. So,
Okay.
but as a substitute for which maybe we could use a similarity transform. So I haven't yet used it, but this was the idea. I think that one of the uses of similarity transform could be this that I yes um, right.
Right. Yeah. Yeah. So that is an alternative approach to diagonal. So you can also define diagonalizability as matrix is diagonalizable if it is similar to a diagonal matrix. So that is another way to define it. So this is similarity transformation, right? So where the similar matrix is D. So A and D are similar. So as long as you have a square matrix that is similar to a diagonal matrix, then it is diagonalizable. So because that is what this is, right? So that is one other way that people usually define diagonalizability as a.
So are you saying that this A equals PDP inverse and that SAS inverse are related?
So yeah, so you can also call this P inverse, right? Sorry, P inverse AP. So you can also call it P inverse AP equal to D. So A and D are similar, whether it is all that's what similarity means, right? Two matrices are similar if you can find a matrix, invertible matrix P, such that P inverse AP is D or PDP inverse is A, right? So A and D are similar here. So here A and D are similar, which is why the change of basis was all discussed, right? So we can in fact define diagonalizability in a third way. So a matrix is diagonalizable if there is a basis in which it can be represented as a diagonal matrix. So for example, that basis will consist of eigenvectors.
If A and D are similar, they will have the same eigenvalues, right?
Yeah, same eigenvalues.
And even the eigenvectors are probably related in some way, although
Eigenvectors not necessarily,
not
but
necessarily
the eigenvalues are certainly the same.
same. Yes, identical.
Okay, so that is diagonalizability, and of course this we already talked about, right? So a power n is that is the whole idea. So p d power n p inverse.
Yes, yes.
So that is something we spoke about.
Although this is a fairly long way of computing powers, even then, right? I mean, it's definitely shorter than doing the whole thing manually for large
Right.
amounts. But even then, I think there, yes, maybe there are faster ways, but I think they are beyond the scope of the course, right? So, for example, one theorem that I mentioned, right, where we basically write the powers as exponents in a equation, something like that, or where basically we treat the matrix powers themselves as uh, what do you call um, like
Kelly Hamilton, you're
yes,
saying.
yes, K.D. Hamilton, yes. I forgot the name.
Right. I'm not sure if that is a shortcut. So what it says is that the matrix solves its own characteristic polynomial, right? So yeah,
Yes,
you do
yes.
end up having these powers of matrices. Yeah, perhaps that is an easier way. I'm not sure. In practice, I'm not sure how they would do
Eventually,
it, but I'm guessing. See, this is easy enough, right? Because it requires only three matrix multiplications. You have to raise once you
um,
raise d to the power. In
yes,
fact, only two, right? So a into d power n, and then that into p inverse.
yes,
Of course.
because that one is fairly easy, right? The T.
Yeah, yeah. So
It's,
all of this perhaps is better explained in numerical linear algebra textbooks. So there they would
okay.
have proper algorithms for it. So in fact, there are a very efficient. This algorithm is never used. So for example, in reality, you can never solve this, or rather, very rarely can you solve for lambda using this equation. So there
Yes,
are
except
right.
maybe if we are using computer, right?
No, even when you use a computer,
Probably
you will
feed some other algorithm.
you will have, yeah, there are actually iterative techniques. So there is one popular technique called power iteration. So there
Yes.
power iteration is a very useful method to
I think this is where we get into computational complexity and things like that, right?
right, yeah.
Yes,
So
yes.
power iteration is one method for finding. In fact, there's one Wikipedia entry also very since this is a very popular method. So
Okay.
you can there is what they do is they repeatedly multiply a matrix with a vector and scale that output. So for example, you take a vector at random a into that vector and you scale it, normalize it, and then you repeat the process. So this is one night you are mentioning, right? One application of fractional eigenvalues. So if your eigenvalues are fractional, not necessarily fractional, but if you have one dominant eigenvalue, this is something the prof also mentions, right? When you have a dominant eigenvalue, you can very easily get hold of that dominant eigenvalue using this method. So
Oh,
repeatedly multiplying by a is what you're doing. So that will ensure that the dominant eigenvalue kind of comes to the forefront while others fade away. And so in practice, that is one method to uh,
yes,
get hold of. Yeah.
this power iteration has a lot of interest.
Right,
Maybe
right.
I'll check it sometime. But yes,
Yeah, so that is diagonalizability. So yeah, what were we talking about? Other thing is if a matrix has distinct eigenvalues, then it is diagonalizable, right? So maybe so just to be clear, if a matrix has n distinct eigenvalues, right, all of them have to be distinct. This is sufficient, as you said. So this
yes.
is a sufficient condition for
A quick check, basically.
yeah, yeah, right. That is diagonalizability. What else do we have? And then the other thing was what GM. AM equal to GM, right? So AM lambda I equal to GM of lambda I,
Yes, this is the proper test actually.
right? Yeah. So for each lambda I, right? So for each lambda I, this has to hold. And if this holds, yeah, this is both ways, right? So if it holds, then it is,
Diagonalizable, and
yeah,
if diagonalizable, then this necessarily holds, right?
right, right.
Okay.
Okay, so that is diagonalizability. What else do we have? We have,
Triangular, some
okay. So,
things around that.
yeah, so for
Yeah,
triangular
we have
matrices,
a point at the bottom. Okay.
yeah, so maybe you can add that there. So for triangular matrices, you have eigenvalues are
Just the diagonal elements.
the diagonals, and what else do we have? The determinant anyway comes from there, right? So product of the, you can, yeah, or you can expand the determinant along the first column, right? That also will work, or says first row, depending on,
Yes, in any column, any row, actually, right?
right? Yeah, so that will lead to once again product of eigenvalues. So determinant is, but this is not a special property. It's just that it is true for every matrix, right? So every square matrix. So else with the triangular matrices, do we have anything else? Uh,
Mm, Probably did, but I think it was maybe not fundamental in the sense that, uh,
okay, okay.
yeah, uh,
Yeah, so the main idea is one thing is it kind of leads up to. So have we discussed unitary matrices in the course by any chance? Unitary matrices.
uh, I'm not sure,
Okay, yeah. If you're not sure,
but,
then I think
from what I covered, I didn't find yet.
okay, okay. Yeah, then let's leave that out. So uh, yeah. So this is so transpose one nice property is that eigenvalues are of A and A transpose are the same, right?
Yes.
So
In
A,
fact, this is how we define symmetric matrices, right?
yeah,
No, I mean, no, actually, sorry, yes. I mean, for that, A equals A
correct. Yeah, A
T.
equal to A transpose. So
So how do you, how does this connect? How do these what is the order of what is the sequence in which these things hold? So we first have symmetric matrices, right? Or
so
do we first have same eigenvalues?
yeah, this is the first one because this is more generic. So it
Uh,
need not be symmetric for it to hold groups, right? So
Yes.
this is
Okay.
always
Okay. This always holds. Okay. Okay.
yeah.
And
Symmetric,
the second one is just a definition. Okay.
yeah, it's a definition of symmetric matrix,
Yes.
right? So
Yes.
symmetric matrices are interestingly always diagonalizable. I hope this we have discussed in the course, right? Have we discussed this part in the course?
Uh, Probably, but I didn't like actually go
Okay.
into
Okay.
it. But
So
I think I know the idea. Yes.
okay. We
Mm,
discussed that in week nine.
Like
What is
lot of these things. I mean, what I do is like manually, like check something.
okay?
So kind of unrigorous, induction, basically.
Okay. Okay.
Uh, which
Yeah.
which if something is established, then it maybe it's fine to just get started.
Right. Right. Yeah.
Yes.
Yeah, so symmetric matrices are always diagonalizable. That is a very useful property. In fact, this is called the spectral theorem. So if we have not discussed this, then I think
Oh,
some point
okay.
of time we discuss.
Okay, I've heard about this. I just don't know if in this course or elsewhere.
Right, right. Yeah,
But probably in the course only.
yeah. So this is a nice property. So symmetric matrices.
Yes. So the are the first and third points related in any way?
No,
Eigenvalues.
this is a slightly more powerful result. So this is one of the central results in linear algebra. So this
Okay, okay.
requires little more work to.
Maybe just mark it in bold or something. Yes.
Yeah. So this requires slightly more effort to prove. So yeah, here, so determinants, I think, yeah, this is that whole expansion of that is, I think, a bit boring, but yeah, that is
Yes.
classical.
Yes, I mean, okay, okay. You are not yet at the
So
properties.
the other thing is what the whole properties, not necessarily
Yes,
prop.
yes, yes. There were some properties like one is determinant of AB is what? Determinant A times B when this,
Yeah, the multiplicative property of determinants and
yes. And then how if we swap the columns or the rows every time we have to multiply by minus one the
right.
result.
Yeah, so
So
elementary row operations.
and also column we can do right swapping
Yeah,
in this.
elementary rows. Yeah, yeah, that
Yeah.
is also allowed. So
We just
elementary.
have to keep track of the minus sign every time basically each time
Right. Yeah.
it do this
So,
thing. Yeah.
swaps changes sign, scaling changes the determinant by scaling it, and the other one doesn't change the determinant at all, right? So adding one time, adding some row times a constant time some other row to a different row, right? So that doesn't change the. Yeah. So those,
Uh,
those are the
so row operations, but wait, row operations do change the determinant.
not all of them, right? One row operation will not change the determinant at all. So
If we just scale it, right?
no. So scaling will change the determinant. So scaling a row also scales the determinant.
Same, okay, by the same factor.
Yeah. So by the same factor. Now swapping also changes sign, right? Swapping changes sign.
And this applies to both rows and columns, right?
Yeah, both rows and columns.
Okay.
Now adding a constant
Adding,
times one row to another row, not to the same row, because if you add to the same row, you could end up getting a zero row. Like I can add
yes.
row one plus minus one row one, right? That is not
But,
allowed.
but
So adding,
yes, but this one we use for solving systems equations also, right?
yeah. So these are the same elementary operations when applied
But,
to
but,
finding
but
determinants.
there the determinant changes. Uh,
No, there also it won't change, right?
I
So
mean, we are not we are never interested in the determinant there actually,
correct, yeah.
but
There
uh,
we are
but
not.
uh, but
Here,
but uh, but it doesn't change. Okay, maybe then I
so
think I confused something.
yeah.
But I
Uh,
think the other instructor maybe once told me, or maybe I got it wrong. I don't know this.
okay, okay. So this
So
this is the only important
it
thing.
preserves the determinant. You are saying
Yeah, yeah.
okay.
So there are few other properties, right? So if two rows or columns are the same, then
Uh,
determinant is zero, right? So this actually follows from these properties. So you can just
yes,
scale
yes. I
and then
mean, for something like this, we can actually just manually check very quickly, right? So if we, but yes, I mean, let's say by taking a three by three, but okay.
right, yeah, yeah. So I think properties. What else do we have?
Inverses, by the way, might be interesting.
Inverses, right? Yeah. So inverses,
Inverses and transposes next.
yeah. So inverse. We know that there is a matrix B such that A B B A I, then A is invertible, right? So A is invertible
Yeah.
if A is invertible if there is matrix B such that, in fact, if A is square, right, only then we are talking about this, right? So even if AB equal to Y, then we can conclude B is the inverse. So we usually present it in this form, but the moment we say that AB is I, we can conclude that A is invertible. So BA will also be I. So the inverses, we know that A is invertible if and only if determinant of A not equal to 0, right? So that's a classic property.
Yes, because otherwise it goes in the denominator, and we don't want to end up with
Right, right.
infinity or not defined. Yes.
Yeah, so there are, I think, many other things, right? If only if A is full rank.
Has adjunct been covered? Because that is the way I used to still calculate the
Yeah, that
uh,
I also don't remember if I think
one,
so.
one, one by one upon determinant of A times
It's
adjunct
2
of A.
o'clock.
Yeah, yeah, I think so. I think that would have been covered. So
Yes, I mean just remember from class 12th, and I use it as much as I can.
correct, correct. Yeah. So
And
this
then
is the
this subject,
transpose of the
yes,
cofactor
and
method.
the transpose, yeah, of the by taking the cofactors. Yes,
Yeah.
yes.
So I think that should be covered somewhere. Right. So
Even if it is not, it's useful. So yeah.
okay, what else do we have? A is invertible if it is full rank. So A is invert. So I think all of A is invertible if only if the columns of A are linearly independent, right? So many things we can say, I think. So linearly independent.
Yes. Yes.
Yes. So what else regarding
Columns
this?
and also rows, right?
Yeah, columns slash
Yeah,
rows.
because it's a full rank matrix. So yeah.
Right, right, yeah. Okay. Yeah, I think that is some of these are some of the most important ones regarding
When we have transpose, they were fairly a bunch of them here. I
yeah
think
trans
they were all class 12 based, but yeah, maybe.
yeah. So the whole there are these whole multiplicative properties, right? So you have a B
Yes.
transpose is B transpose A transpose, and then
Yes.
A transpose is transpose, right? So transpose is A itself.
Simply A.
And in fact, we also have for inverses of, so in fact, A inverse
Yes, yes, some properties of in
or
yes.
A transpose inverse, right? The inverse of A transpose is A inverse transpose. So it's just A inverse transpose, right? So if A is inverted, that is
Yes, of
uh,
course.
right. What else for transpose? Then eigenvalues and
Yes,
eigenvectors.
there were a few more of using both A and B.
Using both A and B. So there are,
Yeah.
yes, that mean the row spaces of AB. So
In the transpose properties.
okay,
Um,
using AB. Uh,
I think you are
AB,
for this. Okay, okay. This.
what else do we have? So multiplicative property is one. This is the most important one because this gets used very often.
Yes,
Uh,
yes, the first one. Maybe you can then emphasize it, although
yeah,
it's
so this is one.
just
Hmm. Yeah, so that is there. What else do we have?
and then we can have like composites based on these few properties. Like I mean, yes, where we kind of parameterize basically in terms. Okay, fine. Which is
Yeah, so there was also this whole idea of row and column spaces of
yes, spaces. There was
product of
something.
matrices, right? So these are actually there was a lecture on this. So you have the column
I
space.
I don't think I watched them, but you
Yeah,
can write the essential ideas.
yeah, just a couple of ideas were there. So the column space of AB, right, is contained in the column space of, so A into column 1, A into column 2, column space of A, right? So this is like A into, so this will, the way it will look is AB will be like A into the first column of B1, so on till A into the last column of B, B, right? So if A and B are, for example, A is M cross N and B is N cross P, so that it's compatible for multiplication, then the columns of B, if you call them B1 to BP, then you have AB. This is one way of multiplying matrices, right? So A into first column of B, that will be the first column of AB itself, right? So therefore, the column space of AB is just a span of these columns. So that is contained in the column space of A. So each AB. So if you look at AB itself, uh, so if you look at, for example, AB1, right?
And
So
likewise, row space of B, right?
yeah, likewise, row space of AB is contained in the row space of B, because because AB you can also write it as a row matrix. So first row of A, so you can call it A transpose. Sorry, yeah.
So space here refers to the span, basically, right? I mean,
Span of the
yes.
columns rows.
Yes.
Okay, so that is that. This for completeness, this is A1 transpose B. So this is the nth row of AB. Yeah, so these were some ideas there. And
Yes.
what else did we have?
Then there were some ideas like how if all these elements are one or zero or other such special cases, which we can maybe do manually only, right?
Ah,
Otherwise, it will be too much to remember.
yeah. So yeah, I can't think of anything else here.
Okay. I'm just taking a look at the um Seek portal.
Yeah.
Uh, Computing powers. For powers, do we have anything more? Like, for example, the property that we discussed in the very beginning, right? How if all the eigenvalues are strictly less than 1, then the matrix squishes down to 0 as the power increases.
Sorry, I lost you. Sorry.
Wait. Uh, okay, I am not on mute. Okay. Yes. Like, are there more properties around powers? Uh, uh, there were some like questions where a raised to the power something equals 0, and then based on that, answer some questions about a. Uh,
Oh, okay. I'm not sure. Can you show me the question? Like which question?
yes, let me just. I think it was week 8 practice assignment. Let me just check. So if I find a question that might prompt you to recall some more things.
Ah, okay. Okay.
I'm still searching. Just give me a minute, maybe. Maybe this was in the graded assignment. Then let me check this. It's the same thing. Let me get this one, and then there's this question. Uh, like for example, if we check this question 9, 10, 11 of the graded assignment, week 8.
Okay. 9, 10, 11.
Yes.
Ah, okay.
I think this one is easy. This right. I mean, if, the 9 one. Uh,
Okay.
although I think the question is not asked correctly, or there should be like because it's asking what are the eigenvalues of a, right, and there could be up to like five of them, right?
Yeah, there could be five of them.
But I think what it is trying to ask is the product maybe or something, or maybe one of the eigenvalues has to be zero, something like that. I don't know, but uh, but I
Yeah.
guess yeah. Like, is this the question well defined? I mean, complete? Or
Yeah. What are so you can yeah we can only ask one of the eigenvalues here.
yes, yes, because the field only takes one input. And then question number 10, I think I got this one wrong. I
Okay, let's try this. So what is a cube is zero, right? So a cube is zero. A cube is zero. Then what are the eigenvalues of a? Okay.
maybe first we write it as BDP inverse thing. Sorry, BD3 BDQP inverse, right?
But
And
uh,
then we try to infer something about D cubed.
but for that it should be diagonalizable, right?
Yes, and that is not given or said.
Yeah.
Okay,
Uh,
so I think let's maybe assume and see if
Yeah, but that may see that may not be. One thing we could do is a cube minus lambda I is we can factor we can factor a cube minus lambda I. So we can, for example, we can factor this as a minus is like a cube minus b cube. So this is a square plus uh, you know lambda square I plus lambda ai, right? So just lambda a. But then
Uh, how did you
so
factorize this? I
this,
mean,
for example, you remember the x cube minus y cube, right? X minus y to this is from
yes. I mean, we don't use these a lot,
yeah,
but
we don't use this a lot, but yeah.
that
So
is why maybe.
yeah, ideally,
But
so this
okay,
is
I now slightly remember. Yes,
okay.
this used.
Uh, yeah, but yeah, this we are not expected to know because this is not standard. So let's stick with a cube. So a cube is 0. So if it has an eigenvalue, it will obviously have some eigenvalue eigenvector. So this is a v is lambda v. So a cube v is lambda cube v. So that much is, and this is always 0, right? So lambda cube v is 0, which implies lambda has to be 0. So
Uh, yes, all lambda. I mean, like
yes, right? Because so if we are given a cube equal to 0, so let uh, lambda v be any
so.
eigen.
So
Uh,
this seems like the trivial. Like, isn't it the zero matrix? Yeah, I mean,
uh,
or
so a cube is 0, right? So if you see, we know that lambda cube is an eigenvector of sorry eigenvalue of a cube, but then a cube itself is 0. So which means that
yes, for finding this, for answering this question, I think we have enough, right?
yeah. So in fact, all eigenvalues are 0. That's why they have asked what are the eigenvalues. In fact, even then it's not. They should have asked what is the only eigenvalue of A.
Yes, yes, because the framing itself is like slightly confusing.
Yeah, yeah.
Okay,
So
and then let's look at question 10. Find the maximum possible value of the geometric capacity.
okay.
And here it comes out as 4 instead of 5, maybe, or 1. Okay, how to think about this?
That is because so that's
But
because
it says suppose a non-zero. Okay, it's written actually non-zero matrix. So that part actually is clear.
yeah. So lambda equal to 0 means so lambda equal to 0 implies A is not singular, right? So or rather A
Mm.
is singular.
Yes. Yes, and not a full rank. Uh,
Yeah. So A is not full rank. So which implies that you cannot have term
linearly independent.
right? Because that would mean it is full rank. Because if we have 5 linearly independent eigenvectors, then that would be
Uh,
5 full rank. So
yes. Okay. So this was also definition based only.
yeah, so therefore it can be at most 4.
At most 4. Okay. And then 11. Okay.
Phase
Okay,
diagonalized.
okay, this one I think maybe I'll leave this on for my own, right?
Yeah, sure. Yeah,
Based on 9 and 10 and everything else that we
yeah,
have.
sure. Yeah,
Okay, okay. Okay, so do we have anything else or shall we close because it's 9:15 now?
yeah. I think that is all. I
Yeah,
guess.
I think all the major at least points we have covered, right?
Yeah,
Please do attach the notes, right, in the
yeah, yeah,
supplement.
sure. Yeah,
Because this will be really handy. Yes,
sure. Yeah,
yes.
I'll
Maybe
attach
those.
it as it is.
Yes.
It's fine, right? You don't want
Yes.
any cleaning up, right? So you
No, no,
can.
no, no, no.
Yeah. Okay.
No. If cleaning up anyway, I can do, right.
Yeah, yeah, yeah.
Just keep any solved problems separate from the list of properties and everything.
Yeah, yeah, sure. So where do we have this supplementary content live session notes?
Yes.
Okay, I'll
Some.
put it here. Yeah, I'll
Yes.
put it here. Yeah,
Yes. Please do it right now only.
yeah, yeah. Okay then.
Great. So next we'll be meeting after quiz 2, right?
Right, yeah.
Okay, there's a session on Saturday, but probably.
No, I think there won't be there, yeah.
Okay. Okay. So
So,
you kind of preponed that to today.
yeah,
Okay.
yeah, yeah.
I can see that. Okay. Okay. Cool then, sir. Have a good night then.
Yeah, sure, yes. All the best, yeah.
Yes. Okay. Thank you, sir.
All right then. Bye bye.
Bye.